going to be talking about building InfluxDB 3 Core, which is the latest release of the open source version of InfluxDB. We call it, it's basically a real-time columnar database and a processing engine that's built on top of object storage. So really I'm going to talk quite a bit about that, basically how do you build a database on top of object storage and what that looks like. So first a little bit about InfluxDB and the use case. InfluxDB is a time series database for metrics and events. So this is time series data, right? This is a dashboard for one of our clusters that we operate. You can see a bunch of different things that we're tracking, like writes and CPU usage and all this other stuff. This is the S&P 500 over the last 5 months. It's a pretty exciting one. That's a time series right there. So basically at its core, time series data is a collection of time value pairs ordered by time with some metadata attached to it, right? So I have some example metadata here, a sensor ID, a host name, a building, a region, a customer, a version of the software that's running, right? You can basically come up with any number of dimensions, and within each dimension, the cardinality describes how many unique values there are for that thing. So some use cases for time series data, like server and network monitoring is an obvious one. Application performance monitoring and custom metrics that you're tracking in your applications. Within sensor data, there are many different little categories, right? You have factories with machines and production lines that you're tracking, power generation, and this is different if you're doing solar versus wind versus a regular, LNG power plant. Mining, water and waste operations, rockets, agriculture, satellites, vehicles of all kinds. And then structured event data, right? Individual events, which people don't generally think of individual events as time series, but you can view them on a timeline and you can actually create time series from that raw event data. Tracing data is another example where you can think of it like time series data, right? Every single span occurs at a certain moment in time. You can look at aggregations across those spans, aggregations across traces, individual traces. Log data is obviously just text blobs and stuff like that, but all of that happens at points in time, and you can, if you want to, induce a bunch of time series on the fly from logs that you have, right? You can say if it's a request log to an API, you can say how many 200s over time there were, how many 200s to a specific endpoint, 200s to a specific endpoint from a specific user. It just goes on and on. So when we talk about time series databases and time series data at Influx, I think of it in two different ways, right? The first one is what people most often think of when they think of time series data, which is you store, a time series database is for storing computed time series data, right? So these are samples that you take at fixed intervals of time. This is metric data. And usually that kind of time series data is essentially, it's not the highest precision view that you have of the world, right? It's a summarization generally of some underlying event stream, right? So if you track your mean response time to an API in 10-second windows, that is a summarization of the raw underlying event stream of each individual request that you service to that API, right? So time series data is basically, if you store that, what you're storing is a summary, and you decide what level of precision you want to store those summaries at. And then the other way to think about time series data is, in a time series database, is maybe you want to actually just store a bunch of raw data, semi-structured or even unstructured data, and you want to be able to compute time series on the fly from that raw data. And you want to do this generally very, very quickly for real-time dashboards and monitoring systems and stuff like that. So the data model for InfluxDB 3 is, looks like a regular database. You have logical databases at the top, you have tables, and then beneath that you have columns. Within the tables, the time in InfluxDB, the time column is a required column always. It is a nanosecond scale timestamp. There are tags, which are basically time and tags together represent essentially the primary key for a table. Tags are key value pairs where the value is a string. That is frequently the metadata that describes time series. And then there are actually the values that you're measuring, right? For Influx, we support int64, float64, unsigned int64, booleans, and strings. We do intend to add basically byte blobs and arrays, structs, and maps, hopefully later this year or maybe sometime next year. But that's definitely something we want to do. So when looking at InfluxDB 3 versus the other previous versions, 1 and 2, this is what the data model mapping looks like. So in version 1 and 2, we had something called a database and a retention policy. In version 2, it was called a bucket. And in version 3, we just call it a database. Then we had something called measurements. That's basically a table. And then you have columns. And with columns, we map the InfluxDB types of tags, fields, and time onto that. We also created Line protocol. We did this for version 1 of InfluxDB. It's just a text-based protocol to write in a bunch of data. We have an HTTP endpoint where you can write data into it, and you can post data to a bunch of different tables. So right on the left, you see you have the table that we're writing data into, you have the tag set, then the field set, then a timestamp. And an individual write request can write data to potentially thousands of tables at the same time, right? It's designed to be able to ingest data on the fly to many, many different tables. So our use cases, some of the properties, some of the things we built for, the first is schema on write, right? You don't have to define even a database or a table or any of this stuff up front. You can basically just send a write request to the database, say, I'm writing to this database, and here's a bunch of line protocol, and it will create the database, it will create the tables, it will create the columns within the tables with their types. And then once it's done that, subsequent writes will be validated against that schema, right? So the schema is set on the first write, and then we look at it. We also have an API to be able to define that ahead of time, but we found that in terms of like people being able to just quickly use the database, this has been a real usability win over the years. So that's been nice. It's high volume, it's denormalized ingest. Most of the value in our use cases is in recent data. And actually, if you look at query workloads, it's frequent that over 50% of the query workloads will be for monitoring and alerting systems, not for humans looking at things. And most of those queries look at the last 5 minutes of information, or maybe the last hour, right? Because those are things that are like performing a check to look for something, and you're looking for very recent context to compare it. So we have this real like fall off in terms of like the value of the data and how frequently people want to look at it. We did an exercise, a couple of years ago, where we looked at our Cloud 2 platform and what people were doing. And there were, I think it was something like 70% of the customers never queried anything more than 24 hours in the past. They were literally just writing data in only for this like recent monitoring and visualization workload. It's a performance sensitive query workload. So these are always for dashboards where people, the dashboards are refreshing once a second, once every 5 seconds or 10 seconds, and they want to see those updates come quickly. Or it's for monitoring and alerting systems. So generally the expectation is queries return in tens of milliseconds or hundreds of milliseconds, but definitely under a second. Anything that takes more than a couple hundred milliseconds, we usually start hearing from people about. We also have automatic data eviction. We haven't implemented this in Core yet, but previous versions of InfluxDB had this. Core will have this very soon, where you can say, for this table, for this database, evict the data after 24 hours or after 7 days, right? So you can just feed the data in, and it will clear it out automatically. And the way the data is organized, it makes it efficient so that it basically can just like drop files as opposed to trying to delete individual rows, which would be very expensive. So the performance expectations of our use cases, data can be ingested in seconds or milliseconds, right? So it's not like a lakehouse workload where you write files up and your expectation is, it becomes available for query within like 5 minutes or so. Our users expect the data to be queryable within a second usually. These queries are also almost all what I call needle in a haystack queries, right? They're generally not queries where you're saying like, do a table scan and compute me some aggregate over all of the data in the table. It's more like, for this time series, get me this hour of data, right? So you're really just asking for, anywhere from 10 to a few thousand values out of, billions or trillions of values that you write in per day, right? So that is the trick, is like, how do you find that and make that efficient and cheap in terms of CPU and memory and all this other stuff? So because of that, usually like we don't optimize for large scale analytical queries or workloads, right? Our goal is we're trying to optimize for those needle in a haystack queries, and the large scale analytical queries are best handled in other solutions, right? In Databricks or Snowflake or Athena or whatever it is you want to use. And our goal, particularly with InfluxDB 3, is to have it seamlessly integrate with those systems so that we can egress the data out in Parquet into Iceberg, right? So that you can query it, do that large scale analytics elsewhere. So this is my best attempt at like a visualization to show what makes time series like tricky and difficult and interesting. So essentially, like, you can think of the data like this, right? T1, this top row, is now. And each of the numbers are basically individual like time series that you're tracking, right? So you record a value for each of these time series now, and that comes in, and then 10 seconds later or a minute later or whatever, the next set of values comes in, and the next, and the next, and the next, right? And if you were just like spooling this data off to disk, this is essentially how you would write it, right? It would be organized like this, you'd be writing them like this. But the problem is, every time you want to query this data, you want to query this, right? So you want to go, basically data arrives wide and you want to query deep, or data arrives horizontally and you want to query vertically. And having the system manage the lifecycle of the data and the organization of the data on disk to be able to make this fast is the entire problem. So the evolution of InfluxDB, we released 1.0 in 2016. This was written in Go. We had our own query language called InfluxQL that looks kind of like SQL. It was good for like people to onboard quickly because it looked kind of friendly and usable, but we found over the years that it was frustrating in some ways for people who are like SQL experts because there were ways in which it wasn't SQL. And we built our own storage engine called TSM, the Time Structured Merge Tree, which is basically a storage engine inspired by LSM trees. Very similar to that, but focused on our use case of time series data. In 2020, we released version 2.0, which used basically the same storage technology that we had built before, but in this time we built it as a multi-tenant SaaS cloud application, which is an entire other talk I can give you about the nightmares of that. And we created our own language called Flux, which was not just for query, but for scripting and being able to put processing into the database. And shortly after the release of 2.0, we started working on what would become 3.0. And we did not, at the time, we did not think we were working on 3.0. We thought we were basically working on a new storage system for the 2.0 cloud product, right? We were trying to, like, our 2.0 product, we didn't focus on the core database engine. For 3.0, our goal, the pieces we were working on, we were focused on the core engine itself, right? The query engine and all this other stuff. So we released the open source build of this last week. So last Tuesday, you can see April 15th. And as I mentioned in this blog post, it's the culmination of a 4.5-year journey. And in that journey, we decided to rewrite the Go database in Rust, which has been fun and painful at the same time. I love Rust as a language, but rewriting your entire project is not something I would recommend people do, but I will at least try to explain why we did this. So it's written in Rust. It's built with what we call the FDAP stack. These are Apache projects that you're probably all familiar with: Flight, DataFusion, Arrow, and Parquet. I'll talk about a couple of these. So why did we do a big rewrite, right? This is like an insane thing to do by most standards. And the thing we had is there are three big problems that we wanted to solve in version 3 of the database that were, ongoing problems from version 1 and version 2, things that our users and our customers had been asking us for years. So the first one is infinite cardinality. They wanted to be able to write data into the database and not worry about the cardinality of that data. Remember this here, the time series, that metadata. The metadata is the drivers of cardinality, right? It's the number of dimensions that you want to track, but also within each dimension, how many unique values there are, right? In container monitoring, you can imagine that the container ID is something you want to track, and obviously that's highly ephemeral and has basically unbounded cardinality because you're spinning up containers and turning them down all the time. Network monitoring is also tricky in cardinality, right? Because you have point-to-point connections and all this other stuff. So we wanted to be able to really the goal is we want people to just throw data at the database and not worry about, oh, am I going to blow up the database because of cardinality? We also wanted a fully capable SQL engine, right? In V1, we had InfluxQL, and we had a bunch of requests of capabilities and things that people wanted to do that you would find in a standard fully featured SQL engine that we just weren't able to support. In V2, we had Flux, where you could do a lot of these things, you could do even more because of the fact that it was a scripting language, but the problem was there was a learning curve and a lot of people didn't want to learn Flux. We did get some fans and some adherents, but really what people wanted was the language they already knew, and at this point the language that it doesn't matter if they know because the LLMs all know it and they can write it for them. So a SQL engine that can do everything, right? As I mentioned, InfluxQL, this is an example InfluxQL query. As you can see, it's not quite, it's similar to SQL, but it's not quite the same. I will say the one thing about InfluxQL that's really nice is if you're doing basic time series queries where you want to group by one of these dimensions or more of these dimensions, and you want to do a summarization of 1 minute summaries for the last hour or whatever, expressing this in InfluxQL is trivial. It's super easy, whereas SQL time series queries are all kind of ugly and suck, in my personal humble opinion. But so for the SQL engine, this was in 2020 that we were making this choice. We picked Apache DataFusion. At the time, so we knew we didn't want to create our own SQL engine from scratch. We wanted to take something off the shelf that already existed, and we evaluated 3 options at this time. This was in May and June of 2020. And the 3 we looked at were ClickHouse, which there was no company ClickHouse at this time, right? That didn't exist. And we looked at DuckDB, and MotherDuck and DuckDB Labs did not exist at that time, right? It was just basically a project out of CWI with some postdocs who were doing crazy stuff. And we looked at DataFusion. And DataFusion was also very, very early too. It was contributed to the Apache Software Foundation in the fall of 2019 by Andy Grove, and largely the entire thing was written by him, and there was no community around it. But there were a couple of things. One, when we looked at these 3 options, none of them had literally everything we needed already off the shelf, right? We realized that we would have to contribute heavily to whatever it was that we adopted. And there were 2 things that were appealing about DataFusion. One, it's written in Rust, and our entire thing was going to be written in Rust, whereas the other 2 are written in C++, and we didn't really want to deal with that. And the other is it's part of the Apache Software Foundation, right? So it has a governance model that we know, right? And at this time, none of us were, we had contributed a little bit to ASF projects here and there, but we had no real involvement here. But our bet and our thesis at this time was if we adopt this thing and we start contributing to it really, really heavily to build our database on it, other people will pick it up and they will start contributing and a community will form around it. This is what I call classic open source strategy, which is you want to commoditize your dependencies, right? Your dependencies are things you have to pay for to deliver your product, but they're not really what differentiate you out in the market from all these other things. And to us, we viewed a high-performance vectorized query engine as a dependency, we knew that everybody was like reinventing this same wheel in literally every single columnar database that existed. So the theory was we're going to try and like juice the commodification of this dependency in an open community. And so far, I think this has actually played out really, really well. I think it's also largely due to the efforts of Andrew Lamb, who is like the PMC and like drives this project forward. But I'm like, of the things we've done in 3.0, this is one of the things I'm most proud of. So the other big thing we wanted to do was separate compute from storage. We've obviously heard this a number of times in this track today. This is the trend. We wanted to be able to separate the two. And where we arrived was this idea of a diskless architecture, right? I put it in quotes because, right, serverless, diskless, they're disks somewhere. But the idea is that we can use object storage exclusively for all data, all state, right? So the servers can spin up. They don't even need a locally attached disk. They can use object storage. And there's some benefits that we get out of this, right? So one, you get multi-AZ durability for free. Also, you don't have to pay the Amazon transfer tax, which for at-scale data projects is very expensive, right? It gets up there in terms of costs. Like your infrastructure costs can get juiced by like 20% just through transfer fees, which is, difficult. It's cheap, right? $23 per terabyte per month, 40 cents per million requests. It's broadly available, right? It's in all three major cloud providers. There are open source projects where you can run it on-prem. There are multi-region options, right? There's this whole like set of tooling and third-party ecosystem around object storage that make it just really nice because like one of the problems we've had in like version 1 and 2 of Influx is basically like they're this island, right? They're this island of a project and also of data. And one of the things we were hoping with using object storage is like we open it up and people can just get at the files. And the other thing that's really, really nice is basically we have stateless servers, which make for a much more operationally simple system, right? So basically, you get object storage and then you spin up the servers and you can go. And then you can actually run a database inside of, say, Kubernetes, for instance, that doesn't totally suck to operate and isn't total pain, which generally I think stateless workloads inside of Kubernetes is. So one other thing that actually happened just this last fall that was super useful, kind of a game changer for us, was S3 finally added put if absent. Which was huge, right? Because then, like, if you read like the Delta Lake paper and all this other stuff, like all these people have done all this hacking over the last like whatever number of years around the fact that like S3 didn't have this. When it has this, you can have multi-server writes into object storage, and you can use object storage as a coordination layer for the servers. And we take advantage of this in our multi-server like commercial product based on this architecture. So the other thing we added was an embedded Python virtual machine. So it's built with this project called Pyo3, Python build standalone. These are Rust-based projects that basically make it so you can embed a Python VM into a Rust thing. And basically what we built is an API within the Python. There's a Python library that this plugin system loads up, and we created 3 things to trigger on, right? So you can trigger on writes, and I'll go through like the write pipeline here in a second. You can trigger on a schedule like cron or whatever, right? Like run once a second, once every 10 seconds. Or you can trigger on an HTTP request, right? So we allow you to bind to an endpoint at API v3 engine and then some string. And basically what it will do is it will yield to your plugin that you've injected into the database the request headers, the request body. Then you can do things like interact with the database, write data, query, and then send a response back. And the idea here, like, obviously, like, you can pair Python code with the database, right? You can spin up your database in Amazon. You can have Lambda functions and stuff like that. But in version 1 of InfluxDB, we had a thing called capacitor, which had its own custom language for doing processing. So this is like a processing agent for doing modern learning. In version 2 of InfluxDB, we had a thing called tasks, which was Flux, the language, whatever. And in both versions, I was actually very surprised at how popular these two things were with a certain set of users and how durable their use has been over the years, right? We still have people who use Capacitor. We still have customers who use it, despite the fact that we maintain it, but we haven't actively developed it in 6 years, I think. So I think there is something to, even though like, yes, you can spin up VMs and put Python or whatever, I think there is something to the like usability and the overall developer experience that you can create if you're able to actually like have a plugin system like this that's tightly integrated with the database. So the write lifecycle. So a write request comes in, we parse the Lime protocol and validate that against the catalog. We do schema validation. Because we're schema on write, we inject new schema into the catalog and save it, and we save it to object storage. And then we buffer that data in RAM into a batch, which is held while we hold connections from the writers. And then we send that WAL file to object storage. So we batch up a bunch of write requests into a single file that goes into object storage. Then we write that contents into an Arrow buffer in RAM so that it's queryable and fast. And then we send a response back to the client that said everything's good. So visually, this looks like this, right? On the left, we have the client. We write in, we validate, we put it into the write buffer, which is this 1 second batch. We send that to object storage, and we send it to the queryable buffer, and we send a response back. The other thing here is that queryable buffer. It's all Arrow data. And once every 10 minutes, we will take that and we'll actually snapshot it into Parquet files that are in object storage, right? These individual WAL files that we're writing to object storage, they are meant to be short-lived, right? They are meant to live only for about 10 minutes as the recovery mechanism in case the server goes down or gets shut down or whatever, before we get a chance to actually write that data as Parquet into object storage. Parquet is the long-term format that we use. So some of you may be wondering, well, it sounds like you have up to 1 second write latency on your writes, and that sounds kind of shitty. That's true. You do have that. If you send a request right after the thing has been flushed, it could be a second, or if you send it right before it's flushed, it could be very fast. Now, the one thing I will say is, again, you have to kind of look at the use case and see what is acceptable to people. This is the most common thing we see in terms of what users and customers have set up that use InfluxDB, right? You have data producers, they write the data into Kafka, and then you have consumers that pull the data out of Kafka, and then they write it into InfluxDB. So basically, the point at which the data is actually sampled or collected or generated to the point at which it's actually queryable in InfluxDB has a variable latency already. There's already a pipeline there. And different people have different tolerances for how much of a lag they're willing to accept. But our theory is basically like, a second is within bounds. The other type that we see is a bunch of individual writers, and all they're doing is write data into InfluxDB, right? They're not reading their own writes, right? That's not a very common thing that we see. It's basically like thousands of individual writers writing data in. Sometimes they'll write it direct into Influx. Other times they will set up Telegraph, which is a data collection agent that we've created in front. And they'll send all the writes into Telegraph, which buffers it up in memory and then sends it to Influx. So in both of those cases, people usually have lagged collection between when they actually generate it to when they write it. But I will say the expectation is usually that they want to get the data within hundreds of milliseconds or a couple of seconds. We did create an option in the write API where the writer can specify no sync, which is basically you can just write the data in, it'll get schema validated, and it'll put it into the buffer and return a success to the client immediately. The downside there is there's a potential for data loss if the object store goes down or the server crashes before it flushes that WAL file out to object store, right? So again, it kind of depends on the use case. Some people can do different things. But Ultimately, seconds from initial collection to readability we found is okay for these things. So I'll talk really quickly about the catalog. So the catalog we keep in Object Store, and it stores this data, right? So what databases exist, the table definitions, and what columns they have, a last value cache configuration. I don't really talk about these two in this talk, but we added two things to this that are new, to InfluxDB 3 that are new. The last value cache, which is basically give me the last value of this time series, and distinct value cache, which is basically get me the unique values for this metadata, right? This dimension, right? Both of these are supposed to drive like faster user experiences. And then tokens, which are basically the security mechanism. And then for our multi-server config, we also store which servers exist in the cluster. But we keep all the catalog data in Object Store, but all of this data is meant to be cached in RAM by every single server that's running. So on the Object Store itself, looking at the catalog in the wall, this is kind of like what the directory structure looks like, right? Every node has a string identifier that you give it, and then beneath that is a catalog checkpoint, a sequence of catalog files, right? Starting with 1, 2, 3, and it just goes up by sequence. And periodically we will checkpoint that so that when you restart, you don't have to read the entire sequence to get it. And then the set of wall files. Now, this setup allows us to have multi-server configurations where the servers don't have to talk to each other to get essentially like a close to real-time view of all the data that's coming into the system, right? So you could spin up a server and say, tail the wall from this node, and this node, and you can get that data as it's written in, modulo, a second of lag time. So the other piece that we have is, I mentioned the expectations for our queries are that they come back in tens of milliseconds or hundreds of milliseconds. What that means is you can't go to object storage for anything if you expect to be within that budget, right? The average response time on object storage can be like 300 milliseconds, and the tail latencies can get really bad. And the thing is, we're never just requesting, we're rarely requesting just a single file, right? So we have to manage the lifecycle of data coming in wall files, landing into the queryable buffer, which is Arrow. And as you can see here in the queryable buffer they're 10-minute blocks of time. So that 10-minute block of time is based on the timestamp of the data, not of when the write came in. So we split it out into those 10-minute blocks so that when we go to snapshot, we take that Arrow buffer and we write it as a Parquet file. So the other thing we do is, when we do that write to the Parquet file, we also keep it in RAM as Parquet. And only once it's actually been put into RAM as Parquet do we actually clear out the queryable buffer, the Arrow buffer. So there's no point at which a query will come in that's looking for this recent data where it will have to go to object storage, right? The cache hit ratio is supposed to be 100% for recent data, right? So snapshotting, I won't go into a ton of detail here, but I just wanted to show the directory structure of object storage. So we store snapshots of Parquet files. So we don't keep the list of Parquet files in the catalog, the official catalog. We keep it in a separate set of files that we can read on startup, so we can see okay, what files exist without having to do list operations against object storage. We do one list operation initially against the snapshots directory and against the catalog directory, but then we're just doing gets. And here you can see the directory structure is, databases, you have a database name, an ID, a table name, an ID, and then you have the date, these 10-minute blocks of time, and then a sequence number and just a Parquet file. So querying looks like this. Basically, a query request comes in. We validate that query request against the catalog just to see all the metadata is there and it exists. We pull the record batch or batches from the query buffer, and then we filter the Parquet list that we're going to look at based on obviously the table and the time range that we're looking at. And then we pull those Parquet files from cache or object store, and we brute force a query over it. Before I get into the complications of brute forcing a query on Parquet, I did want to just show an example of like the cluster setup that we can create based on this. So this is actually in our commercial product, not in the open source. But basically, like, because we have the object store and we have this diskless architecture, none of the nodes basically talk to each other directly. The only thing they talk to is object store, right? So we have total isolation in terms of what happens if you query a node and you crash that node, right? It's completely isolated from everything else. And it also means that we can scale independent pieces independently, right? We can scale up the compactor or scale up the writers or scale up the query layer independently of each other. So the cost, right? One of the reasons we did this whole like object store thing is it's definitely like a cost optimization thing. And it's not just about the transfer fees, right? There's, you know, things about like how expensive BBS is and stuff like that. And one of the things is like, why are we writing a wall file once a second? Well, once a second wall file is basically $13 per month per writer. And through config, we have a flag where you can like reduce that. But if you reduce it to say 100 milliseconds, it's going to get a lot more expensive. So tables, if you're only persisting on this like, you know, one file per 10-minute block of time and the data's coming in, you know, as it arrives with those timestamps, you're looking at about 2 cents per month per table that you're tracking. But again, that's only if the writes come sequentially. One of the other tricky things for us is, you know, it's very common for people to have thousands, tens of thousands. I've seen hundreds of thousands of tables in schemas for people who use InfluxDB, which that would quickly get unmanageable in terms of expense. But we have a plan, which I'll talk about. And ultimately, all of this is only if we can actually buffer 10 minutes worth of data without having to flush it out to object storage because of memory pressure, right? So the other drawback to this kind of style is we end up getting large resource spikes at 10-minute intervals of time, right? Because when we do the persist, we take that Arrow data and we actually run it through a DataFusion plan where we sort and dedupe it and then write it in. So you see like in our usage profiles, we see like big CPU spikes and network spikes to send all the data to object storage. So these are things that as we built this, we're kind of like finding as we test it more and more, these are like problems we need to solve that we need to optimize for. So gets are actually really, really cheap, which is nice. But when you think about it, every 10-minute block in every single query is a get if you don't have it cached, right? So if we were to have a no cache system and you have a lot of queries coming in, that could get very expensive very fast. So caching is critical for high throughput situations where you have a lot of queries per second. So I also wanted to talk about optimizing the file layout for queries, which is, I think that, ultimately like what makes time series tricky. So to do this, you have to compact the data, right? And every like big data system has some way of compacting data to reorganize it. You compact so you can reorganize the physical layout to optimize for queries, but also to process row level deletes, right? A lot of these systems, they operate where the file is immutable. If you want to delete, you're going to rewrite whatever file that row appears in. And then the other piece we have is basically indexes outside of the Parquet files that help us map to, specific things that we're indexing on to narrow it down to which Parquet files we want to look at. Or we haven't done row group indexes yet, but in theory, that's part of the plan, right? Because remember, data's arriving horizontally and we want to query it vertically. So we basically want to reorganize it so that this vertical query is efficient. So the first bit is compaction of the time blocks, right? So in the top row, we have these 10-minute blocks of time, and that's what it would look like. So if we're gonna query this 160-minute block of time, we're gonna hit all 24 of those blocks up top. Or if we have this compaction, in this example, we're just gonna compact into 20, then 40, then 80, then 160-minute blocks. Then if we want to query the entire time range, what we're looking at is actually the last one should be lit up too. So we're going to query 5 files instead, right? And the number of files you have to deal with can frequently have performance impacts on your queries. So that's one reason to do it, is to organize it into larger blocks of time. And this becomes really useful if you're doing analytical queries across like all of the data in a specific time range. The other thing is basically to index the data. So within the database, we have data organized into what we call generations. We picked generation as the name rather than levels, because levels is kind of like it's an overloaded term. Like people understand levels to be a certain thing, and we didn't want people to bring that preconception to this thing. So we're just calling it a generation of data, which I think is in the time kind of idea. So here we have a generation, which is a 24-hour window of time. And on the second row, what we can see is like, this would be if we arranged that data by time. Like we just had blocks within the generation that are time ordered blocks, right? So that's one way to arrange the data. But the other way would be to arrange it by some other sort, some key that you're sorting on, right? So it could be like a sensor ID, or it could be a hierarchical key like, country, state, city, and then, sensor ID. And basically you get the lowest row, which is to organize that data by that first and then time, which for us is a better situation if we pair that with a posting list that says, hey, if you're looking up where column A equals foo, we know that occurs in this one file, right? For this 24-hour window of time. Whereas if you didn't have the lowest, the ABC organization, if you wanted to query for where column A equals foo across this 24-hour window of time, you'd have to hit all 24 files if you had 1 per hour. So I'll close with some lessons from this. I think I'm closing in on time, but so the InfluxDB style schemas for, I would say, Parquet is not great for us, right? As I mentioned, like it's frequent that people will have hundreds or thousands, actually thousands and tens of thousands of tables is quite common. And many of those tables, the data is wide and sparse. Right, we have people with potentially thousands of columns or tens of thousands of columns, and it's not like for every row, you have a value for every single thing. So wide, sparse tables with many, many thousands of tables, like the way we've modeled that data in Parquet it's not very good, definitely in terms of like how we ingest the data into object storage and the reorganizing of that data. So we may, we're looking at evolving how we do that. Many thousands of tables, I mentioned these. More indexing is basically going to be required, right? We have needle in a haystack queries, and we need more indexing to be able to look those things up quickly, because the best way to answer those queries is to have a map where you can say, here's the data, as opposed to doing a brute force calculation over some like large chunk of data. We also need to look at using a local disk cache to save money, right? Like RAM is extraordinarily expensive to keep all of that data cached, but the problem is like people aren't willing to accept the performance hit that only having the data in object storage gives you. So we definitely need to look at like how can we utilize a locally attached disk to make that faster. And the data reorganization is absolutely critical. For our use case, to compact this data, to reorganize the data, the assumption is for every piece of data that you write into the database, it's going to get rewritten like 5 times or 6 times or more. And optimizing how that rewrite happens it goes a long way towards saving money on infrastructure and CPUs and all this other stuff. So there's a lot of work we're going to be doing there. I will say we found that Parquet support is uneven, right? There are different capabilities of Parquet or different versions or whatever, and different downstream providers have an ability to maybe read or not read those things, right? Nanosecond timestamps, that's what we have. That's not readable by by a large number of people, right? We added it to the Iceberg spec, I think last year or whenever it was, but it's still not, the downstream people haven't picked it up yet. Dictionary encoding in Parquet has been a problematic thing. So we basically, like right now, we have a feature to basically export the data to Iceberg. And originally, like our dream for this was, we use Parquet, we use object storage, and we can just point them at the Parquet files. But the reality is we are rewriting the data. We have to read that data and rewrite it into a different Parquet file that is actually consumable downstream. So we're actually we're not living the dream in terms of Parquet. So some hot takes on this. Apache Arrow Flight, I don't think is a win for usability. This may just be a temporary situation because the client libraries aren't mature and all this other stuff. But honestly, if you're not moving millions of rows around in a request, people just think a HTTP endpoint with JSON back is easier to work with. Parquet is a standard like SQL is a standard. It's a bunch of different flavors. And I think basically if you're going to use Parquet as a data exchange format, you have to design for lowest common denominator. But if you're building a system for a specific use case that's supposed to be specialized, lowest common denominator is at odds with what you're actually trying to do. Arrow is memory hungry. I mentioned this before, right? We have to snapshot the data from the queryable buffer. When we convert it from Arrow into Parquet in memory, we save a bunch of RAM because it's in Parquet. So, not much we can do about that. But I like to call DataFusion Visual Basic for databases. It's probably dating, it's definitely dating myself. Visual Basic, Microsoft did this. It was huge in the 90s. So many business applications got built with Visual Basic. It made a bunch of people programmers who were never going to be programmers without it. And basically what DataFusion is doing is it's basically creating this Cambrian explosion of databases. A bunch of people are becoming database people who never would have been database people because they can pick up DataFusion. They don't have to write the planner and the optimizer and all this other stuff. And I think DataFusion also enables innovation at the edges, right? It makes it so that you could try different query languages and use the execution engine, or you can try different file formats. I think I'm at time. What? Couple of minutes? Okay. I had one more slide where I was going to talk briefly about some ideas, but so yeah, this is kind of where I'm at right now, and this may evolve. But right now I'm thinking maybe Parquet is just best kept for data exchange, and you just use the simplest form of Parquet, right? It's like CSV, but better. So we are currently working on a new storage system where Parquet is not at the heart of it. Parquet will remain in our stack, obviously, for data exchange and stuff like that, because we have a goal of being able to do that. But some of the things about the file format we're investigating, we don't put any of the metadata in the file. We already have the metadata in the catalog. We have uint64 identifiers, and those are cheaper to move around and look at. Many databases and tables into a single file. Column families to be able to have wide and sparse tables. All of the data is organized explicitly for doing compaction with the assumption that we are going to compact every single piece of data, and we're going to do it multiple times, and we need to make that as fast and as cheap as possible. Indexing is optional. So we want to have indexing to enable this, but the thing is we can't. InfluxDB 1 and 2, indexing was an all-in approach. You couldn't opt out of it. The indexing was there, and if you had high cardinality data, everything would fall all over and explode. So making different indexing pieces optional and still figuring out how to store and work with high cardinality data is critical. So Bloom filters, using those extensively, which I know are in Parquet, obviously, and you can use those, but caching of different kinds, cardinality limits, so basically saying okay, we are going to index something, but once we see it get past a certain cardinality, we stop indexing and we actually just fall back to Bloom filters. So that is all I have. So thank you.